This is convolution example number 2. Convolve a finite length sequence with an infinite length sequence. We have a linear time invariant system with impulse response h of n. The input to this system is x of n, and we'll take a look at the specifics of those functions later on. We want to find the general closed form equation for the system output y of n. Because this is a linear time invariant system, then we know that we can convolve the input with the impulse response to produce the output. The convolution sum looks like this. It can also be written in the alternative form, where we interchange the arguments of x and h. The impulse response is of infinite length, whereas the input is of finite length. We'll be using the flip and slide interpretation of the convolution sum, and I'm going to choose to apply the flip and slide procedure to the finite length sequence. Therefore, I'm going to use this form of the convolution sum. In part B, we will take our closed form equation and evaluate it for specific values of alpha and beta at specific times. I'll recommend the calculator for that. And then we want to create stem plots for x, y, and h. Computer plotting tool works well for that. All right, let's get down to the detailed solution. I'll begin by coming up with a stem plot for h of n. Now we're really taking the product of two functions, alpha raised to the n, which looks like this, and the step function u of n. I'm specifically drawing for the case where alpha is a positive value between 0 and 1. Now h is actually the product of these two. That means that every place where the step function is 0, then the product is likewise 0. We therefore see that the impulse response is 0 up to time 0, and then it's a decaying exponential after that. X is composed partly of the difference between a delayed step function or shifted step function. And by the way, if you want to make sure you understand why n minus 5 shifts this, we know that the step function becomes a 1 for the argument greater than or equal to 0. So if I look at the argument n minus 5 and compare that against 0, then we see that n is in fact greater than or equal to 5. When we take the difference of these two, all these areas where we have common 1s, those are going to cancel out. So u of n minus the shifted u of n minus 5 leaves us with this pulse, which multiplied by beta n gives us a decaying exponential pulse, but it's truncated. All right, let me take the impulse response and the input and place those over here. Now our impulse response is infinite length, but the input is finite length. Now we know that the output is the convolution of the input and the impulse response. The convolution sum looks like this. Now using a graphical interpretation of this convolution sum really helps us to better understand how to structure the rest of the solution. I'm going to change the argument for x of n to x of k. Then when I change the sign, that has the effect of flipping x to the other side. Now I'm going to add in the index n. Now for my current picture, n is specifically the value 0. n equals 0 would be located right here at the origin. N equals minus 4, or n minus 4 would be back here. Now, if I change n to the value -1, let's see what happens. N becomes -1. N minus 4 becomes -5. And we see these 2 points shift one place to the left. So that slides x back one place. Now, for a general case of n less than 0, we see that x would be shifted back on the left side. All right, now let's do the same thing for h of k. Now, we want to evaluate the product of x and h, and we'll be summing all of the places where we see a non-zero value. Now, as long as n is less than 0, we have no overlap. That tells us that our output is then 0. Now, let's allow n to increase, that is, allow time to advance. And when n is equal to 1, we have overlap at a single value. So we see that partial overlap is beginning at n equals 0. If I let n increase all the way up to 4, that's where the partial overlap would end. So we have this intermediate region of partial overlap. Let me put this back a little bit so we can more clearly see this notion of partial overlap. Now, as I evaluate my convolution sum, we see that k always starts at 0, because prior to that, the product is always 0. We end up at n. Now, x of n minus k would be our beta with its argument evaluated at n minus k. In a similar way, we evaluate the argument for h for n equal to k. Now let me expand that term, and since n is not associated with our summing index, I can bring beta n out front. Beta to the minus k is actually the reciprocal of beta, so I can tuck that underneath. And at this point, we recognize the geometric series, and we can invoke the closed form of that geometric series. We take the argument, alpha over beta, raise that to the initial index value, which in this case is 0, subtract the argument, and raise that to the upper index plus 1. We then divide by 1 minus the argument, alpha over beta. Now, of course, anything raised to the 0 power is just 1. And here we have the closed form solution for partial overlap. So let me start to collect my results up here. Now, as we let n increase beyond the value 4, and I'm picturing this specifically for the case at n equals 6, but generally we can think of this plot as representing n greater than 4. Now we have complete overlap, and that will change slightly the way we handle the start and stop points of our summation. K always starts at n minus 4 now, but it still ends up at n. Everything else is just the same as what we did earlier. So I'm going to jump ahead just a little bit by recycling the work that we did earlier for the closed form solution. The one place where we have something different is the argument raised to the starting point index, which would be n minus 4. So this expression is valid for n greater than 4. All right, let's bring these all together. That would be the end result for part A. Now in part B, we want to evaluate the closed form solution at specific values of n and for specific values of alpha and beta. You have to make sure you choose the correct form. This would be the form that we use when n is equal to 0. We see that the numerator and the denominator are the same in this case, so y of 0 is 1. Now we move on to n equals 2. Choose that same middle form again, drop in the specific values of alpha and beta, and punching that out in the calculator, I get 1.48. The third value, y of n equals 10. Okay, we have to make sure we pick the appropriate form. This is the third form here. Again, I'll put in my specifics for n, and specific values for alpha and beta lead to 0.75. And my calculator gives this value right here. Collect all those results together, and that's my answer for part B. Now in part C, we want to construct stem plots for the output, the input, and the impulse response. Here I have a LabVIEW math script that I've put together that uses alpha and beta as inputs, and then it calculates arrays for h, x, and y. The LabVIEW front panel looks like this. For alpha is 0.6. This is, again, our decaying exponential. Beta is similar, except it's truncated, so it goes to 0 at this point. And we see y of n has this particular shape. We can spot check and confirm that these values, such as 1, 1.48, and 0.0583, sure enough, they look pretty good from the plots. And then finally in part D, I change the sign of beta to a negative value. H stays the same. With the negative sign, x now takes this alternating sign sequence. Every other value is negative. We see that the output demonstrates this similar alternating sign as long as we have partial overlap. In the area of complete overlap between x and h, we see that it looks more like a traditional decaying exponential. It has to do with the fact that the sign flips cancel in that complete overlap region. All right, that wraps up this problem.